So, good afternoon, everybody. My name is Viivi Uurtio. I am a doctor of computer science and I currently work at Elisa as a data scientist. Before joining Elisa for about a year ago, I researched in a machine learning laboratory at Aalto University. And my research was mainly about unsupervised learning strategies, and I applied kernel methods to compute distances between objects in high-dimensional spaces. And I also focused on validating unsupervised learning models. In the following, I will give a presentation on capturing anomalies from operator network data, a project that we have been doing together with Elisa's daughter company, Polystar. So if we first talk about the general learning tasks that we are dealing with. So we are getting unlabeled data, so we need to detect anomalies from that in an unsupervised manner. Well, what is an anomaly? It is something deviating from the general behavior of the variable or dimension. If we look at this data matrix here in this picture, we see that our observations are on the rows and they are labeled by these capitalized letters. These letters do not indicate anything whether it is an anomaly or not. They just tell some characteristics about these observations. We have now here 5 different dimensions. And if we think that we were working with just 1 dimension or 2 dimension, it is very easy to visualize these points on a 2D or 1D plot, and in that case it's also relatively easy to detect these which are anomalous from the general behavior of this system. But whenever we start working with higher dimensions, we cannot anymore visualize the occurrences in this space so that we could actually interpret what we see. In this case, it is good that we can apply machine learning algorithms to process this data. What machine learning does, or any kind of anomaly detector that we apply, it basically ranks these observations by an anomaly score, and the higher the score is, the higher up in this table they get. So in the end we get a ranking, and the ones that are on top are the observations that are most anomalous or that we should take a closer look at. In the case of if we're working with telco data, maybe some alarming things in the network. So if we look at the outline of this presentation, we are first going to take a look at this operator network data, from where it's obtained, and just some general properties of that data. Then we will think of applying just a single detector, and we will consider some of the limitations of just applying a single detector in this task. In order to improve reliability of the detection output, we could use multiple detectors, because the problem with applying just a single detector, and when we are out of labels, we never know how well the detector actually performed. And finally, we will discuss some ideas of how to select these detectors out of the multitude of detectors that we have out there that we can choose for our learning tasks. So if we now take a look first at this operator network data. So it is probe data or sensor data collected from different parts of the network. This is a very simplistic figure, so those from telecommunications probably have a bit more detailed figures. But the general idea of an operator network is that there is this radio access network and a core network, and in this radio access network we have the base stations that are located all around us, that when we make phone calls or send SMS to each other, these base stations pick up the signals and then they process this information further to the core network. But things that are more interesting probably to data scientists and machine learners is that this data is multivariate. We actually have multiple different data sets from different parts of the network. It is time series data, so the observations are also dependent on the time of occurrence, and it is aggregated, that when a subscriber generates a signal, it actually comes as a binary vector. But when we aggregate it over a certain period of time, we get then the sums over different variables in these observations that we then process in our data analysis pipeline. If we now take a bit closer look at what the data actually looks like when data scientist gets it. So here is an example of operator network data from 2 different time points. And we see here that, well, now we have denoted these observations by the term event 1 or event 2, but in general we have quite extensive labeling on these observations. Basically we have there the cells or the locations, the time points, the subscriber category, traffic category, a lot of things that we can do to identify them, but these labels do not indicate whether it is an anomaly or not. We have as dimensions, well, these also vary depending on which part of the network you have obtained your data, but in this example we have call answers, call drops, call attempts, some things that we want to record from the subscribers when they generate these signals. If we think what an anomaly is in an operator network, it is a change. So for instance, in the case of event 4 here, we see that yesterday there were just 2 and 3 call drops and call attempts recorded, but when we look at the same event today, these values have clearly increased. And this could be an anomaly, but when we do a machine learning model, we also need to consider how far back in the events do we want to look at. In this example, our training set is just yesterday's data, and our test set is today's data, and we want to rank these today's observations using an anomaly detector. So the output of the detector would be something like this, that it could be something like this. Event 4, event 7, event 2 are the most anomalous ones. But if we think that we have, for instance, 35,000 observations to rank, and we just apply a single detector, we can never really be certain that are these that are on top of this ranking list the ones that we should pay attention to, or did we actually miss some of important observations or occurrences that are lower in the lower end of this list. In that sense, we can never actually assess the performance of the anomaly detector, whatever anomaly detector we select. So for that reason, we could take some use of ensemble learning, which is normally used in supervised learning. We of course cannot do any backing and boosting types of things, but what we can do is that we can stack several detectors together so that we would get this kind of London tube map looking kind of plot. And the idea also in ensemble learning is that we want to increase the prediction accuracy by combining several diverse detectors. And in this case, we want to increase the reliability of the detection result. So one option also is to do this parallel coordinates plot using the rankings of detectors. And the benefit of that approach is that every detector generates these anomaly scores in their own way. They are not comparable to each other as such. And if we just were examining these anomaly scores, we would have to do some kind of thresholding that these are, based on this detector, these are anomalies, and based on that detector, these are anomalies. So we can then skip that if we just look at the rankings. And from ensemble learning, we could also use this majority voting strategy, that if we want to further process the information from this parallel coordinates plot, if we want to have just a single final ranking. But this looks nice, but we still have a lot of anomaly detectors that we can choose from. And in most cases, if you just select at random some anomaly detectors and you build this parallel coordinates plot, you will get something like this, that if you first select one detector and put that ranking and use that as a frame of reference for the rest of them, they do not agree with each other. This is actually doing the opposite thing than increasing the reliability of the result. One reason for this could be that these detectors are measuring the data space differently. What this means actually is that if this first detector here is some kind of standard anomaly detection technique, it could be local outlier factor, principal component analysis, isolation forest that examines the space by Euclidean measures. If you have then selected for your other detectors something that transforms the data, such as kernel methods or neural networks, that could explain why this disagreement has occurred. One hint that one could apply when trying to mine for the ground truth is that if the problem is very low dimensional, these standard techniques using the Euclidean distance measure could work very, very fine, and they probably will also agree with each other. But whenever your problem gets very high dimensional, kernels and neural networks could work well. The thing is that when you want to find an agreement between kernel methods and neural networks, you need to find a matching between the hyperparameters of these methods. There are matchings, but you need to actually search for them. And one approach that one could apply here are simulation studies, that you generate anomalies in your data and you generate a complete data set for yourself. In that case, you know which observations are then anomalous, and you can then deduce from that result you can then deduce which detector would be suitable for your problem. So what we have been discussing in this presentation, we checked first what operator network data looks like. We saw that it's very high dimensional. And we noticed that applying just a single anomaly detector never really gives us a certain result. They could all give different results if we always apply just a single detector, but we should mine for further if we want to find the ground truth or the actual anomalies in our data. And the trick for finding some ground truth or probable ground truth in your data is this mining for common measure of similarity, common measure of distance. And that could be found using kernels and neural networks that do transformations on your data, or it could be also using standard techniques that apply just Euclidean distance measures. And we discussed also that in the case that you are not finding this matching, you could apply simulation studies to help understanding how these detectors work. So this is an ongoing research area, and no clear answers are when you are doing with unsupervised learning algorithms. This is a general problem, whatever unsupervised problem you are trying to solve, but we will keep on working on this. So, thank you.